Have you ever really stopped to think about what happens inside your body every time you cough, or laugh, or lift something heavy? All that immense pressure, how do we not just, well, burst at the seams? Deep down in our abdomen, there's a potential weak spot called the inguinal canal. And for centuries, we thought we had a pretty solid understanding of how our body keeps it sealed. But what if that was only half the story? Okay, let's dive right into this. So the inguinal canal, it's this super important passageway, but its very existence creates a fascinating engineering problem for the human body. See, it needs to be open enough for things to pass through, but at the same time, strong enough to keep our insides from, well, pushing out. So how on earth does our body pull off this incredible balancing act? For a very long time, the answers seemed totally settled. Alright, so let's start with the classics, the textbook explanations. These are the really clever, dynamic defenses our bodies evolved to protect this potential vulnerability. I mean, this is the stuff that's been taught to medical students for decades. The traditional view is that there's this whole series of 5 coordinated muscular actions that just spring into effect whenever that internal pressure spikes. You can think of it like a super sophisticated, living security system. We're going to walk through each one because, honestly, they're brilliantly clever. First up, we've got the flap valve mechanism. This one works because of the canal's slanted or oblique path. Because the entrance and exit aren't right on top of each other, any increase in abdominal pressure naturally shoves the back wall against the front wall, squishing the canal flat. It's a beautifully simple defense. It's like stepping on a garden hose. The pressure itself actually helps seal the passage. Next, there's the shutter mechanism. So here, you've got these arching fibers from 2 key muscles, the internal oblique and the transversus abdominis, and they contract together. When they do that, they literally pull the roof of the canal down towards the floor, just like you'd pull down a window shutter. It's an active contraction that really narrows the whole opening. The exit point of the canal, called the superficial ring, has its own special defense, the slit valve. The opening is basically just a split in the muscle fibers of the external oblique. So when this muscle contracts, it very smartly pulls the 2 sides of that split together, effectively pinching the exit shut. Simple, but effective. And then we have the guarding of the rings. This is kind of like having a dedicated security guard posted right at the canal's entrance. The deep inguinal ring, where the whole thing begins, is directly protected by the internal oblique muscle. During any kind of strain, this muscle contracts and actively squeezes the ring, reinforcing it against all that pressure. And finally, number 5 is the ball valve mechanism. Now this one is fascinating because it actually uses the contents of the canal as part of its own defense system. The cremaster muscle contracts and it pulls the testis and spermatic cord up, which then acts as a partial plug for the superficial ring from below. It's such an elegant solution. But here's the big question. Are these 5 mechanisms really the complete picture? So just when it seemed like the story was complete, some new research started asking some pretty tough questions. The thinking started to shift. Maybe all these dynamic actions rely on something much more fundamental, a structural element that we had pretty much overlooked. And this quote from the surgeon Dr. M.P. DeZarda just nails the problem. He basically observed that a key structure these classic defenses rely on, the transversalis fascia, is, and I quote, papery thin without any strength. I mean, that's a huge deal, right? It raises a critical question. If the very foundation is that weak, how can the rest of the system possibly hold up under all that pressure? This observation led to some really good, pointed questions. Like, think about it. Why don't babies, who are crying and straining constantly, develop hernias even if their shutter mechanisms aren't even fully developed yet? And why do so many hernia repairs actually work, even when they don't specifically try to restore these classic defenses? These little inconsistencies strongly suggested that something else had to be at play here. The answer, according to this newer research, isn't found in how the muscles move, but in what the wall of the canal is actually made of. This is where we introduce a new hero into our story, a hidden layer of pure structural reinforcement. And this hero is a set of aponeurotic extensions. Okay, so what's an aponeurosis? Just think of it like a broad, flat tendon. It's not muscle, it's a tough, fibrous sheet. The theory is that this strong layer, which comes from the transversus abdominis muscle, sits right in front of that papery-thin fascia, creating this really robust 2-layered wall that provides the real baseline strength. And the evidence for this is, well, it's pretty staggering. In a study, they looked at 30 inguinal canals from people without hernias and 30 from people with hernias. The findings couldn't have been more clear. Every single one of the healthy patients, 30 out of 30, had a full, strong covering of this aponeurotic shield. Now get this. In the group with hernias, None of them did, not a single one. 24 of them had it completely absent, and the other 6 had a really weak, deficient version. Looking at the actual photos from the operating room makes it even more powerful. Okay, on the left, you're seeing a healthy inguinal canal. See that strong, white, fibrous layer? That's it. That's the aponeurotic shield, providing a solid back wall. Now, look to the right, a canal with a hernia. The difference is just night and day. That protective layer is thin, it's patchy, or it's just plain not there. Let's look at this diagram to really see how it's supposed to work. Okay, so number 8, that's the weak transversalis fascia we talked about. But look right in front of it, labeled with the number 12. That is the aponeurotic shield. It's a strong, structural barrier that seems to be providing the real, actual strength to the posterior wall. So does this new theory mean the 5 classic mechanisms are just wrong? Well, not necessarily. What it might mean is that we're finally seeing the complete architectural blueprint for how our body really prevents hernias. So here's the key takeaway. What we really have are 2 complementary views. The classic mechanisms, they describe the physiology, the dynamic, moment-to-moment actions of the muscles. The aponeurotic theory, on the other hand, describes the underlying anatomy, the fundamental structural integrity that makes those actions effective in the first place. Here's a good way to think about it. The classic shutter and valve mechanisms, they're like actors in a play. They can perform their roles perfectly, but if the stage they're standing on is weak and flimsy, the whole performance is going to collapse. The aponeurotic shield, that's the strong, solid stage. It provides the foundation that's absolutely necessary for all those dynamic defenses to even work. This whole story is just a fantastic reminder that science, even something as known as the anatomy of the human body, is never truly settled. It really makes you wonder, doesn't it? What other fundamental truths that we all take for granted are just one curious surgeon or one new study away from being completely rewritten?